Hello, everybody. Today we're going to start our presentations for people's projects. So today will be the 508 students. Um, so what we're going to try, if this works today, is to do this through Zoom. A couple students from 408 said that in 426 and Chemi 426, you all are doing PowerPoint recordings, and I think that that's a reasonable option if students prefer to do that, especially if they want to do like a multi-person presentation. That probably would make a lot more sense. So I handed over control of my screen to Charles, who might be, wait, I think. So Charles, I think you may have gotten a notification of to control my screen. So go ahead and accept that. Okay. So yeah, so Charles is a graduate student in the chemistry department and works for Professor Wenyu Huang. And he's going to be talking about some of his issues, I guess, or challenges that he's had with regards to nucleating catalyst particles in some porous materials. So Charles, go ahead and feel free to start.
Okay, thank you. So yeah, my name's Charles. Like you said, I'm a second year grad student from the chemistry department. And for my final project, I decided to look at some modeling of metal adsorption and nucleation and deal with that a lot in my line of work, and something I've never really dug too deep into, but I thought this would be a good chance to do so. Okay, so for some of the goals of this project, I wanted to do some analysis that could maybe lead to better control over this metal loading process that I do. I want to do this to minimize the wasting of precious metals, which is kind of like the whole theme of my work anyway. I want to use these metals as efficiently as possible. Maximize control over the incorporation and monodispersity of these metals, and essentially make an efficient and repeatable material synthesis. So this material synthesis I'm talking about is shown on the right-hand side of the screen. My support or surface, you can think of it as, in this case, is this ZIF8. It's a type of MOF. I typically expose this to some form of metal precursor solution. In this case, it's palladium. I deal with a lot of platinum, rhodium, metals like that. I then reduce this metal to form metal nanoparticles on the surface of my support. From there, I normally use it as a catalyst. There's a bunch of other things you could do with it. But in my case, I'm focused on catalysis. So I want these particles to be stable. So that way I have a stable and recyclable catalyst, along with monodisperse. So that way I get good yield, good activity, stuff like that. Okay, so this is what my material should look like in most cases, right? This is the product of that scheme I just showed. You have your MOF crystal. On the surface, these darker spots of this TEM are the rhodium nanoparticles I use. So you can see they're all approximately the same size, spread out. That's what it should look like. On this slide are some TEMs of bad batches, right? Like, materials that won't work for my uses. On the left-hand side is a TEM of that same type of material, except note that there's a lot of crystals with no metal on it, or very like 1 or 2 nanoparticles on them. So that means it's a much lower metal loading, and that means most of my metal went somewhere else, right? I can't use it like I want to. On the right-hand side, similar theme, showing that it's not very stable on the surface because you still get a lot of these empty crystals. But then in this lower right-hand side, you see nearly all the rhodium has gathered around a few crystals. It's not spread out. It won't be a good catalyst. So that's why I wanted to study stability, monodispersity, stuff like that. Okay, so for the methods of how I broke this down, I used a 3-step metal loading mechanism. So first, adsorption of the metal precursor onto my surface, followed by the nucleation and then growth of those particles. So that's just what this image down here shows. Typical generic example of this process. So yeah, I broke it down in those 3 steps, but I only modeled adsorption and nucleation for this work. And I did it in a way where I could vary certain parameters that I could control during the synthesis and then predict the impact it would have on my material. I wanted to model the best conditions to meet my goals. Some things I could change around are surface area, percent metal loading, temperature, concentration, things like that I could control pretty easily during the synthesis conditions. Okay, first I'm going to talk about adsorption, and this is what it looks like in my material. On the right-hand side is just what a unit cell of my crystal looks like. And on the left-hand side is a zoomed-in version of what the surface looks like. And you can see the metal precursor binds to, in this case, zinc or whatever other metal I'm using as the support. And that's how the precursor is adsorbed to the surface. Oops. Okay. So in order to model this, I use Langmuir's adsorption isotherm. Some assumptions and details about this is that he treated the adsorbate as an ideal gas on an ideal solid surface. That he treated adsorption and desorption as a reversible process that you can describe using an equilibrium constant. Using the assumption that there's 1 molecule per adsorption site. And this model also ignores interactions between the adsorbed molecules. So on this image, I'm using this top left-hand one where all the sites, adsorption sites are the same, and there's 1 molecule per each of them. Okay, so now for the actual equations that I used to do this, I didn't go through the derivation or anything like that, but this is the main one up here. I'll break down all the variables. It relates QE, which is the adsorption capacity at that equilibrium I was talking about. It relates that to the concentration of my precursor that's still in solution, CE. And then QM is the max adsorption capacity. So if it was like 100% full, what would that capacity be? And then that KL is the equilibrium constant I was talking about. So to approximate a value for QM, I took the surface area of my support divided by the surface area of the precursor to find out what the maximum possible loading would be with 1 molecule per 1 site. Next, I had to find a way to approximate this KL value because both CE and QE are like experimental values, and KL is based off of those. How you would find it is plotting CE versus CE over QE. Take the slope divided by the intercept, and that is your equilibrium constant, and describes that adsorption desorption process. I use literature values in place of experimental data because I don't I don't have this data. So yeah, I used those approximations to set this up. All right, so some of the results. The first thing I looked at was plotting CE, excuse me, versus QE. And this is the type of, this is isotherm I would use to see if my model follows my experimental data. So I could use like ICP or something like that to measure these values, plot it against this model, see how closely they match to each other, okay? But this is the expected curve. Next, I wanted to see how my absorption capacity at equilibrium related to my initial concentration of metal, because that's one of those parameters that I could screen, I could play around with when doing the synthesis. So I used this equation. It relates that same QE to the CE value, molar volume, the mass of my support, to the CO, which is my initial concentration. So I held everything else steady and varied that initial concentration and got a plot that looks pretty similar to the last one, but it shows us that as you add more metal initially, your absorption capacity will increase, which makes sense. The more metal you have, the more that's absorbed, but also that the rate, the efficiency of the absorption slows down. You can kind of think of that as the slope of this graph, right? The steepest slope means it's the most effective, the most efficient. As it starts to level off, that means more and more of your initial metal is staying in the solution rather than being used and being deposited on the support. So that was one way I use this model. And the next one, I studied the impact of changing that QM value. So in my actual material, I could do something to increase the surface area. I could cause defect sites, something along those lines, to increase or decrease the maximum absorption of my material. And there's a linear relationship between the QM and the QE, which once again makes sense. As you increase the possible, the actual will also increase. So for absorption, I plan on using some combination of these models, my experimental data, to continue studying how efficient my metal loading process is. All right, so that's it for that section. Next, I looked at the nucleation. This is defined as the initial process that occurs in the formation of a crystal from a solution, a liquid, or vapor, so on and so forth. The key point is the initial process. So I am treating this separately from growth, as I'll talk about in a second. But we have two types of nucleation that can happen, homogeneous and heterogeneous. Both of them involve these atoms or molecules coming together to form a particle that creates a new solid liquid interface. And then growth mechanisms take over from there. So to model this, I use the classical nucleation theory. This theory treats particles as droplets with well-defined surfaces and surface energies. It states that there's a free energy barrier associated with particle formation. I'll talk a little bit more about that on the next slide. Also states there's a critical size for that particle to be thermodynamically stable. It's too small and it'll just redissolve back into solution. I used it to relate the critical radius, change in free energy, to the rate of nucleation. I'm interested in how fast this process is happening, when it's happening. This theory also states the system will work to minimize its free energy and that nucleation is separate from growth. So like I said, I kind of wanted to study the rate of nucleation for my process. So I wanted to be able to predict this based off a couple different parameters. I want to make sure that absorption is complete before nucleation begins. So that way I have as much of my metal as possible on my support, and heterogeneous nucleation happening before homogeneous. Okay, so now I'll talk about what is homogeneous versus heterogeneous. This image on the left, the top row is an example of homogeneous. It's particles in solution combining together once they've reached that critical size and they overcome that energy barrier, they form this new particle marked as yellow. It's one particle now. And then that can grow, right? On the bottom is heterogeneous. It's the same thing, except it happens on the surface, which is desirable in my case. The right-hand side shows a plot of this proposed energy barrier. And it shows that heterogeneous nucleation is more likely, which is good for me because due to this energy barrier gap, right? It's much easier to overcome that in the case of heterogeneous nucleation. Okay, so modeling this, there's this initial equation that relates that the change in free energy to the rate, which is this dN dt variable. And then I use a further derivation that relates a couple different parameters I can control, such as temperature, the saturation of the solution, and the surface energy. And then some other variables that are necessary in here is Boltzmann constant and the molar volume. Okay, so my results for this. I wanted to see how this rate was dependent on temperature during this process. So I plotted temperature from just about 0 Celsius all the way up to higher values. And you see that as you increase the temperature, you increase the rate. That makes sense because you're providing more energy to overcome that barrier, so it happens faster and faster. Okay, that has its pros and cons. It might be beneficial because it will happen faster. You'll be more likely to have homogeneously sized particles. But in my case, it also may lead to more homogeneous nucleation happening, in which case those particles are just growing in solution and will either be wasted when I wash my material, or they will deposit on, but it could be different sizes. So it's got its ups and downs. So I wanted to look at how I could change something other than temperature so I could have a fast nucleation, but still keep it at low enough concentrations that my particles stay small. So that's why I looked at this saturation dependence of the nucleation process. And as you increase the saturation of your solution, I would expect, this shows me that I would expect the rate of nucleation to increase as well. So using a combination of, once again, these two models, I could find a happy medium between too much metal precursor and too slow of nucleation, a bunch of different variables to play with in this case. All right, and so to kind of conclude, I created some basic models for portions of the metal loading process, studied how some of these controllable parameters impacted the results. I mainly focused on the adsorption efficiency and nucleation rate because those are the ones I'm most concerned about with my current projects and future projects as well. And then I could continue building on the scope and complexity of these models, right? Keep adding variables, keep adding interactions, things like that. And I could supplement and test them with experimental results. So that concludes my presentation today. Thank you all for listening, and I'll take any questions you have.
Thanks, Charles. So we got one question from the audience, and whoever else has some questions, you can feel free to put them down in the chat. Lauren has a question She asked, why does heterogeneous nucleation need to happen before homogeneous?
So it's not necessarily heterogeneous before homogeneous, but just in my case, I want as many of the particles on the surface as possible. So I want heterogeneous nucleation to happen before adsorption. Adsorption to happen before nucleation. So that way they're already on the surface and they stay there throughout.
Could you explain maybe why that's good for catalysis?
Yeah, so catalysis is all about, at least in my case, having a stable catalyst. So that way you can recycle it through multiple reactions. And then you also want to have the highest possible surface area of your active site. So the smaller my active site is and the more spread out it is, the better.
So Calvin in the class asked the question, can you discuss the applicability of this to things that we can actually conceptualize in real life? What sort of industries or technology would these metal loading processes take place? And I think that you mentioned catalysis, but I think maybe considering that most of the class may not understand or have a good understanding of these sort of supported catalysts, maybe it would be worth going back to your picture of ZIF8 and explaining what that is and why you're doing that exactly. Does that make sense? You have a few minutes, so you probably have some time to do that. It'd probably be good for the class.
Yeah, that makes sense. And just keep in mind, chemists, not engineers, so the don't think as much on the large scale and industrial process, at least right now, mainly focused on just the academic side of it, right? I think you actually have control of the screen.
Oh yeah, sorry. Let me move back to your picture of ZIF8 that you have back. No, this is something else, right?
Yeah, keep on back.
Sure.
So yeah, this will do. This will do. So to answer your question, I'll give you the example of probably the project I've worked the most on so far is trying to create a catalyst for hydroformylation. I know it's a pretty big industrial process that is kind of a feedstock for a lot of different chemicals, a lot of different functional groups. So essentially, how this would be applied is I would have these metal nanoparticles on this surface, or sometimes you could put them on pretty much anything, right? And then your reactants come down, interact with that metal on the surface, and then leave as your products, right? This is beneficial compared to homogeneous catalysis, because in homogeneous catalysis, you have problems separating your catalyst afterward, right? So in this case, I'd be able to reuse this material over and over again, rather than right now, it's mainly based on homogeneous catalysts where they use them once at a large scale and then they're pretty much done. So that leads to higher costs because that's done using rhodium, which is very expensive, and then just kind of a waste of materials, right? So if I were to apply this in industry, that'd be how it would be useful. I think that answers your question.
So I have a question. So you sort of talked about this idea of you want to make particles in this ZIF8, and you mentioned MOF, which probably students in the class don't understand what that is.
Yeah.
Could you explain what ZIF8 is, and I guess how, MOFs in general, and why is ZIF8 special, and why are you using it for this?
Right. If you could actually go to the other image of ZIF8 I had, then I think that'd be more beneficial. Yeah, keep on a couple slides. The first adsorption slide.
This one?
Yeah, perfect. So a MOF stands for Metal Organic Framework. ZIF is just a subset of that. They're more like zeolite, so it's a mixture of a zeolite and a metal organic framework. But this is kind of how it's set up. This is ZIF8. It is a zinc-based MOF, so that means these blue nodes you see are zinc metal centers, and they're connected by an organic linker. And there's like thousands of different combinations of metals and linkers you can use. I'm using ZIF8 because well, way down the line, I want to make rhodium mixed with zinc as my catalyst rather than just rhodium. So this will act as my zinc source. Additionally, it has these really small pores. It makes it a more selective process overall. Additionally, ZIF is relatively stable compared to a lot of other MOFs. You can take it up to higher temperatures, expose it to harsher conditions, and it will still stay intact. So that's what ZIF-8 is and why I'm using it.
Okay, I think that we probably should move on to our next presentation. So thanks, Charles.
Yeah, thank you for all the questions.
Okay, so I'm going to hand this over to Ifan. Just give me a second to hand control over to you. So Ifan, you should be getting a sort of notification to take control over my screen here. And whenever you're ready, you can start. So Ifan Zhang is a graduate student in mechanical engineering, and he's going to be talking about some of his work for materials for lithium sulfur battery materials.
Yeah, thank you for Dr. Pantany's introduction. So my name is Ifan Zhang. I'm a first-year graduate student in mechanical engineering. So in the past semester, I'm now working with my professor on kind of soft materials, and we would like to apply these materials on the cathode for lithium sulfur batteries. So I would like to use this final project opportunity to share with you what I have done in the past half years and do some prediction to the further steps. So
is everything okay?
I can't just make the transfer, so could you please show me how to switch to the next slide?
So you should have control over my mouse now. So if you just click, you should be able to get through this.
Okay, I see. Thanks. So I have divided my presentation into 3 parts. So the first part, I would just make a brief introduction about the lithium-ion batteries, including the lithium sulfur batteries. And the second part, I will show you how we design the materials and how we fabricated them. And in the last part, I will put on some analysis about what we have done and make some evaluation of where we will go in the future on our cathode. Oops. Okay, so right now you can see it almost from everywhere. The lithium batteries are very popular in our daily life. So such as in the portable devices, for example, the cell phones and laptops, and even some companies like Tesla are putting a lot of efforts on developing the electrical vehicles. And also even some power plant are using the lithium-ion batteries to generate electricity. And from some source on the energy marketing, so you can see from the figure that 10 years later from now, the demand of the lithium-ion batteries will be almost 10 times more than we have right now. So that's will become increasingly popular in our daily life. So why does that happen right now? So basically, the reason is very simple. So for the lithium metal, it has a extremely high theoretical specific capacity, and the density is really low. That means that you can just pair it with some high potential cathode materials, and we just use them with a small amount of weight, and such device can just supply a great amount of energy density. So another important factor is that the lithium-ion batteries can show some high, a very long cycle life, which means it can be very competitive in some portable devices. And this picture shows you some obvious comparison between the lithium-ion batteries and some traditional battery systems like the lead acid. So right now, the lithium-ion batteries shows a very high power and energy densities. So among the members in the lithium-ion batteries family, the lithium-sulfur battery is one promising secondary rechargeable lithium batteries, which is drawing many scientists' attention nowadays. So basically, during cycling, the sulfur can be reduced and paired with lithium ions to form some lithium sulfate as a final product. And the advantages for the sulfur is that not only for this theoretically high electrochemical performance, and also its abundancy on the earth and the cleanness will also meet some environmental protection requirement. So okay, so every coin has two sides, right? So during the cycling, the sulfur will be finally reduced into the lithium sulfate, but during the cycling, there's a bunch of lithium polysulfide. We call it lithium 2 sulfur X. You can see here there are 4 examples of polysulfide species will be generated during the cycling. And the bad thing is, these 2 species, lithium 2 sulfur 8 and lithium 2 sulfur 6, are really highly soluble in the electrolyte. And right now, the lithium sulfur batteries, the electrolyte is commonly used by the DOL and DME combination of the organic solvents. And these 2 are very soluble in these 2 organic solvents. And sometimes these 2 kind of species will go back and forth between the electrodes, and that will cause some loss of the active materials, which is sulfur in this battery system. And more seriously, this kind of effect, we call it shuttle effect, will sometimes cause some failure of the battery because of the short circuit by this kind of notoriously shuttle effect. So in the 20 years development of lithium sulfur batteries, so in the beginning, people are trying to use some porous structures. On the one hand, this kind of materials will facilitate the diffusion of the electrons and ions in the electrodes. And also it can just have some abilities in trapping the polysulfide species. So such as the graphene and graphene oxide and carbon nanotubes, carbon nanofibers can also do the work. So to further increase the porosity and even create some hierarchically porous structures. So people sometimes use volatile organic solvents such as toluene to use them as a kind of sacrificial template and remove them after material processing. But the carbon is a nonpolar species, and that kind of characteristics really limited its ability to trap the lithium solid polysulfide, which is a kind of polar molecules. So to further improve the trapping behavior, so right now people are trying to dope some polar molecules such as the alumina and titanium dioxide. These are 2 examples of what people have done in the past. So based on this idea, so in the past semester, I have prepared some oil in water emulsion with the graphene oxide hydrogel with a toluene as the oil phase, and picked up a reasonable surfactant, which is 2020. I will explain why I pick up this surfactant. And right now we have achieved kind of a reduced graphene oxide aerogel. So this kind of image right here. So probably in the next step, I would like to dope something on the reduced graphene oxide. And this idea comes from the one of the paper I recently found that some scientists used this silicon nitrides and put some ammonium chloride and silicon chloride to the crucible and doing the same heat treatment with the reduced graphene oxide. And after these reactions, this kind of silicon nitride will be doped on the reduced graphene oxide aerogel, such as this sandwich structure. So in the last part, I will just put on some analysis to this system. So first, I calculated the surface tension between the toluene droplets and the water in the situation without any surfactant in it. So this model comes from the chapter 17 in our textbook. So for the two immiscible liquids, so the surface tension will be the sum of the surface tension of each single phase minus the contribution from the dispersion force. So the final result should be about 53.7 milliNewton per meter. So to lower down this surface tension, so according to some literature, so for the toluene water system, so the HLB value, which is a abbreviation from the hydrophilic lipophilic balance, and this number should be more than 15. So for this, for a certain surfactant, you can just consult some literatures about the HLB value of a certain surfactant, or you can just calculate them with either of these two methods. So based on that, the HLB value of the 2020 here is 16.7. So it is reasonable for us to reduce the surface tension to make a stable emulsion system. So with the application of the surfactant and 0.2 millimolar is the concentration I used in my experiments. And according to this figure, you can see the surface tension will be reduced to about 10 milliNewton per meter, which is about 1/5 of the original number. So another thing we can do to make sure the emulsion is stabilized by our system is the zeta potential. So this is a kind of model we are really familiar with. So from the image I took on the microscope, so I can just assume some droplet size and distance between these two droplets. And the pH here is concentrated by the graphene oxide because there are some functional group that will provide some protons in the water. So the boundary condition is just like our textbook says. So the overall interaction will be more than 25 kT to stabilize the whole system. And the interaction constant is also involved here. And we just need to determine how much potential, I mean, the psi naught, we just need to determine this range to determine how we can just stabilize this emulsion system. So this is my final result with some calculated van der Waals interactions. And finally, I got this zeta potential should be more than about 9 millivolts to maintain a high stability of the whole system. For the next part, I would like to just briefly introduce some predictions of our next step. And after we dope this silicon nitride to the reduced graphene oxide, they will form a kind of sandwich structures. You can see from here, the reduced graphene oxide layer will be packed into the silicon nitride layers. So to discuss with the interactions between these two layers, we can just calculate the overall Hamaker constant, which is a kind of model in chapter 13. So these constants are the are, I mean, these constants comes from certain literatures, and based on that, this Hamilton constant is right here. So we can just assume the interlayer distance is about 0.5 nanometers. So, oops. Okay, so the final result here between these two layers will be about above 400 millijoule per meter square. So this is a very large energy compared to what we have met in our course. So in the last part is about the interactions between this lithium polysulfide species with the polar molecules silicon nitrides. So in reality, people use some models like density functional theory, but it's too complicated for me to show you right now. So I would like to just simplify this model. So basically, we can just use these two sulfur atoms, which will have some interactions with the polar molecule we doped on our host. So there are basically two sets of the sulfur nitrogen bonds. So based on that, the interaction between the lithium polysulfide species and the polar molecules silicon nitride is about 6.82 electron volts. And this kind of number is about 15% higher than what people commonly calculated in the density functional theory. But yeah, above all, it's a kind of simplified models. It will be justified later in my research, I think. So based on that, I draw some conclusion that right now we have successfully prepared the graphene oxide aerogel with the emulsion system as a precursor. So this silicon nitride is kind of a example for us to pick some polar molecules to be doped on our host, which is a reduced graphene oxide. So in some real experiment, we can show some trapping behavior of the cathode materials by some simple experiments, so, as they show here. So on the left side is some high concentration lithium polysulfide solutions with some organic solvents, and we can just add the same organic solvents on the right side and separate them with the cathode materials. And after some times, you can see from the color change from the right side. So if there is barely change in on the right side, you can say that the cathode materials has a kind of very strong trapping behavior to the polysulfide. So I think that's all for the presentations. Thank you for your time, and feel free to ask me some questions.
Thanks, Yvonne. I don't see any questions in the chat, but if anyone else has questions, please feel free to put them in so I can moderate this. But I had a question. So I guess why? So what's special about silicon nitride for batteries?
I mean, this is kind of an example to show how we can just modify the reduced graphene oxide. So in the, I mean, this kind of polar molecules, you know, so probably we can just choose other kind of polar molecules to be doped on the reduced graphene oxide to be served as the cathode for the lithium sulfur batteries. So this is kind of just an simple example to show here. So
okay, and the other question I had is, you have this enormous like energy here, right? Between the silicon nitride and graphene oxide. So I guess, well, how do you interpret this? So this is an attractive energy, right?
Yes. So so could you please go back to the previous slides? So probably this slide will give you the answer. So so based on this model, so you know, the dielectric constant from the reduced graphene oxide is much higher than we have met in the lectures. So if we just apply this model to calculate the Hammond constant, it is also much larger than some simple examples we have met in the course. So so I can just say that these two kind of a nonpolar layer with a kind of a polar layer can form a very strong interactions between each other. So that based on this prediction, so we can just predict that some polarized layer can be successfully doped on the host materials.
Sure. Yeah. So what you're saying is it should very strongly interact.
Yeah.
So I guess the question is then, like, you have a distance in this model, right? So how like is there that you so how exactly did you go about estimating this? Like that we're using?
So I just make some simple assumption based on this SEM images took by some teams in the paper I found. So so I hope that this kind of parameters I assume are reasonable for calculations. So probably.
Okay. So does I guess I don't see any questions from anyone else in the chat, but I think for both of you, I think I will probably give you some comments privately to help keep you moving on this project. But I liked your presentations, and I guess I'm looking forward to the ones coming up on Wednesday. So I think we're right about at the very close to the end of class. So I guess we can end here.
Okay, thanks.